Good morning everyone. I am Annapurna, working as an assistant professor in the Department of ECE at Institute of Aeronautical Engineering. Today we are going to study about digital voltmeters. What is the need of digital voltmeters? What are the different types of digital voltmeters we have? Already we have discussed some of the digital voltmeters. These digital voltmeters are mainly used to get the output without any noise and without any distortion to get the output with more accurately. We are using these digital voltmeters and we have different types of digital voltmeters. With the help of digital voltmeters, we can measure the voltage directly or we can convert frequency to voltage or time period to voltage. So we have different types of digital voltmeters and we have already discussed about integrating type of digital voltmeter and real slope integrating type of digital voltmeter, staircase ramp type of digital voltmeter. Now we are going to study about successive approximation type of digital voltmeter. This is the block diagram representation of successive approximation type of digital voltmeter. In the successive approximation type of digital voltmeter, we have different blocks like start and stop multivibrator and ring counter, control register, DAC, sample and hold circuit, input attenuator and reference supply voltage and digital output. These are the different blocks present in successive approximation type of digital voltmeter. Coming to the multivibrator, this multivibrator is mainly used to generate the pulse signals. Here we have start or stop multivibrator. Whenever we start the multivibrator, it is going to generate the pulse signal. If we stop this multivibrator, it stops sending the pulse signals. And coming to the next block, ring counter. This ring counter is mainly used to count how many number of clock pulses we are passing through this one. That is counted with the help of ring counter. And this control register is mainly used to store the digital output. This is a gate whether to allow the digital input or discard the digital input. We are using this gate. Next we have comparator. As we already know that the comparator is mainly used to compare the given two input signals. If the two input signals are having same voltage, then it allows the gate to open. Similarly, if the two input signals are different, then the comparator sends the signal that the two inputs are different. Like that, we are using the comparator to compare given two input signal. If the two input signals are having same voltage, then the gate is opened. If the two input signals are having different voltages, then the gate will be closed. And next one is sample and hold circuit. As we know that if you are having any input signal, that input signal is continuously varied with respect to time t. For example, if you consider a sinusoidal signal, this sinusoidal signal is continuously varied with respect to time t. At one instant, the amplitude of the signal is 0.2 means at another instant it is 0.3, 0.4, 0.5. Like that, time to time the amplitude of the input signal is continuously varied. If the input signal is continuously varied like this, it is very difficult to compare the input signal with output signal to get the digital output. That's why instead of taking this continuous signal, here I consider the samples. Consider the sample of input signal. That is, if this is the input signal, the input signals are sampled and the amplitude of the input signals are equalized. So, in this case, the input signal amplitude levels are maintained as constant. At this point, the input signal is 0.2, next instant 0.4, next 0.4, 0.2, minus 0.2, minus 0.4, minus 0.4. like that. The input signal having maintained certain voltage level, so that we can compare the input signal with output signal without any loss or distortion. That is the purpose of sample and hold circuit. Next, coming to the input attenuator. This input attenuator is mainly used to attenuate the unwanted signal. Whenever we transmit the signal, the input signal consists of some sort of noise and some disturbance. Those noise can be avoided with the help of input attenuator. Only the required amount of input signal will be transmitted to the next stage. That is the purpose of input attenuator. These are the These are the different blocks present in successive approximation type of digital voltmeter. The name itself indicates that successive approximation. So we are going to approximate the input with the reference signal. As already we know about approximation. For example, to discuss about this approximation, for example, consider a block. This is unknown block and we don't know the weight of this unknown block. And consider one more block. This is the known block. This is unknown block. We don't know the weight of this unknown block. And this is known block having the weight of 1 kg. So, if you want to compare this unknown block with the known block with the unknown block, first of all, to measure the unknown block weight, always we need to compare unknown with the known weight. So, here we are comparing this unknown weight with the known weight of 1 kg. When we compare these two, this unknown weight is greater than that of known weight. This unknown weight is greater than that of known weight. Then we have to change the known weight to 2 kgs. Again, we are comparing the unknown weight with the known weight of 2 kgs. Again, this unknown weight is greater than that of known weight. Again, we need to change the known weight to 3 kgs. Now, do the comparison between unknown weight and known weight. Now, we can conclude that this known weight is greater than that of unknown weight. Now, known weight is greater than that of unknown weight. As already we know that the known weight is greater than 2 kgs and less than 3 kgs. So, we are changing the known weight to 2.5 kgs. Now again, we need to compare this unknown weight with the known weight. If you compare this unknown weight with the known weight, now these two blocks are having same weight. Then we can conclude that the unknown weight of this block is 2.5 kgs. How can we obtain this unknown weight? Means continuously we are comparing this unknown weight with the known weight. Initially the known weight is, we are assuming it as 1 kg known weight. We are comparing 1 kg known weight with the unknown weight. Next, by this comparison, if the unknown weight is greater than known weight, we have to increase the known weight to some another point. Like that, we are increasing the known weight till the unknown weight is equal to the known weight. Whenever this unknown weight is equal to the known weight, then we can conclude that is the unknown weight parameters. From this, we can say that we can find out the unknown weight with the help of approximation. The same approximation procedure is followed in this successive approximation type of digital voltmeter. So, for this purpose, initially we are applying the input voltage to an attenuator. Now the input signal is attenuated with the help of attenuator. So, the amount of attenuation depends upon the next stage. So, depends upon the requirement, the input signal is passing through this block and the remaining input signal will be attenuated here. Then, by using sample and hold circuit, we are equalizing the weights of the input signal. Now, this is the input signal which we are applying to this comparator. The another input signal we are giving to the comparator is from the control register. So, for this control register, initially The data present in the control register is 0. Before starting this operation, we made that control register, the data stored in the control register is 0. Now, we start the multivibrator, we give the signal as to start the multivibrator. As the multivibrator is started, it sends the pulse signal. Whenever the multivibrator sends the pulse signal to the ring counter gives the information to the control register. Whenever the control register gives the signal, then whenever we give the pulse, the same information is given through the ring counter. Then the control register sends the signal as 10000000. This is the information which it is given to the DAC. Now, with the help of digital to analog converter, the input signal is converted into, the digital data is converted into analog and that is given to the one of the input for the comparator circuit. Now the two inputs for the comparator is input signal coming from the input section and another one is the signal coming from the control register. Now the digital input we are applying to this comparator is Vin, which is equal to 00110011. See here, this is the input we are applying through the input section and the input we are applying through the DAC for the first pulse is 10000, 10000 3. So when we compare these two signals, we can conclude that the output voltage is greater than that of input voltage. See here, D7 signal is here it is 1, whereas in the input section D7 is 0. Now we can conclude that the DAC output, that is V output voltage is greater than that of input voltage. Whenever the output voltage is greater than that of input voltage, then we have to reset that D7 bit to 0 and then the next pulse is applied. For the next pulse, we have to reset because input voltage is less than output voltage. If the input voltage is less than output voltage, we have to reset the 7th bit. Then D7 becomes 0. Next, we are applying the next pulse with the help of multivibrator. For the second pulse, if we apply the second pulse, then the D6 bit is changed to 1, 0, 0, 0. Now, again compare input voltage with the output voltage. In this stage also, input voltage is less than that of output voltage. So, again we need to reset D6 to 0. Then, if you apply the third pulse, the 5th bit position is equal to 1. So, now compare this output voltage with the input voltage. If we compare the output voltage with the input voltage, then we can say that input voltage is greater than that of output voltage. If input voltage is greater than the output voltage, then no need to reset that particular bit. Up to that point, the bit position is as it is. Next, apply the next clock pulse. If we apply the next clock pulse, the next bit position is also equal to 1 and then the remaining bits are 0. Now, in this stage also, we need to compare the input signal with the output signal. If we compare this output with the input section, we can conclude that here also the input voltage is greater than output because the input voltage is 00110011, whereas output is 00110000. In this case also, input voltage is greater than that of output voltage. So that keep the first 4 bits as it is. Next, for the next clock pulse, we have to set next bit position to 1 and the remaining 3 bits are zeros. Now, compare this output voltage with the input voltage. In this case, the output voltage is greater than that of input voltage. So, reset the bit position to 0. Reset the bit position to 0. And for the next clock pulse, the bit position is 1. Again, compare the input voltage with the output voltage. The same operation is present here. The input voltage is 00110011. When we apply the first clock pulse, the first bit position is shifted to 1. Now compare this input with the output. The input voltage is less than output. We have to reset the 7th bit D7 and set D6. Again compare this with input voltage. So, in this case also the output voltage is greater than that of input. So, reset the 6th bit position and set T5 to 1. Now, this bit is compared with V input. In this case, the input voltage is greater than that of output voltage. So, set D5 bit as it is, and for the next clock pulse, the 4th bit position is 1. Now this is the output, this is input. Again compare the input voltage with the output voltage. In this case, input voltage is greater than output voltage. So D5 bit, D4 bit also keep it as it is. That is D4 also present in set condition. Now for the next clock pulse, D3 is set to 1. Again compare this with the input voltage. In this case, input is less than output. So that change the bit position to 0 or reset D3 to 0 and say for the next clock pulse D2 bit is set to 1. Next compare this output with the input. In this case the output voltage is greater than that of input. So that we need to say reset this bit position to 0. So for the next clock pulse D1 is 1. Now compare this output with the input. In this case, the input voltage is greater than that of output voltage. So, again, set D1 bit as it is. And again, for the next clock pulse, D0 bit is set to 1. Now, if we compare the input and output, the input voltage is equal to output voltage. Or then, this input and output both are same. So, in this case, if we observe that if the input voltage is greater than output voltage, no need to change the bit position. Bit position is present in the set condition only. The input voltage is less than the output voltage, then we have to reset that particular bit position to 0. That is the process present in the approximation. Each time when we apply the input voltage, for every clock pulse, the output voltage is half of that of the present voltage. Initially, the input voltage is 5 volts. For the first operation, for the first pulse, that is 2.5 volts. For the next pulse, it is half 1.25 volts. Next, for the next clock pulse, it is again half from the 1.25, 0.625. Like that, for every one operation, the output voltage is halved. Finally, after completion of this approximation, the output voltage, becomes 0.99785. Finally, we are comparing that the input voltage and output voltage both are same. Whenever input and output both the voltages are same, then the gate will be opened. Then with the help of This delay counter, we are transmitting the number of clock pulses through the SAR, and how many number of clock pulses passing through this SAR will be counted with the help of ring counter, and that is displayed on the display unit. This is the way how we can find out the output voltage with the help of successive approximation type of digital voltmeter. The main process involved in the successive approximation type of digital voltmeter is this SAR operation, this comparison. This comparison is made between the input and output. Here we are assuming that the input is 0011 0011 and initially the output is resetted to 0. When we apply the first clock pulse, then the first bit position is 1, then the remaining all bits are zeros. If the input voltage is, this is input and this is output. If the input voltage is less than output voltage, then we have to reset the particular bit position. If input voltage is greater than the output voltage, we have to mark the bit position to 1 as it is. If the input voltage is less than output voltage, we have to reset the particular bit position to 0. If input is greater than output, we have to set that particular bit position to 1. Based upon this operation, for the number of clock pulses for these 8 clock pulses, finally we can compare the input signal with the output signal. Whenever input and output both are same, then the gate will be opened and then the multivibrator can send the number of clock pulses through this SCR, and finally with the help of counter we can count the number of clock pulses. That digital information will be displayed on the digital output. This is successive approximation type of DVM. With this successive approximation type of DVM, we get the accurate digital output in the output section. These are the different types of digital voltmeters we have, and these digital voltmeters are helpful to measure the voltages and to convert time frequency to voltage, and we can convert time to voltage. This is first one, integrating type of digital voltmeter. Here we are finding out the frequency. Finally, with the help of integrator, we can measure the output frequency. Here the integrating type of digital voltmeter. In this, with the help of integrator, we are increasing the input voltage, and then we always compare the input voltage with the reference voltage, and finally we can measure the digital frequency. And in the dual slope integrating type of digital voltmeter, we are using two types of inputs, that is we have both positive input voltage and negative input voltage. That constant input positive or negative, that is integrated with the help of integrator, we get the constant slope, that is compared with the zero detector comparator, and finally we can find out the time. This is dual slope and this is staircase type of digital voltmeter. We directly measure the output voltage with this, and finally we have successive approximation type of digital voltmeter. In this case also we can measure the output voltage. With this, all the digital voltmeters are completed. Thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.